Imagine you're a doctor, like way back in 1854.
Okay, setting the scene. That is a pretty grim time to be a doctor.
Totally grim. You're staring at this map of a city, and people are dying from this terrifying, invisible disease, and you're just frantically trying to find a pattern in all the chaos.
Right, cholera.
Exactly. But then hold that thought and imagine a completely different scenario. Fast forward to like 2017. You are a video game developer.
That is a wild jump.
I know. Stick with me. So you're a game dev, and you are pushing the absolute limits of a microchip to render this, photorealistic, billowing storm cloud moving across a virtual sky.
Pushing the hardware to the brink, yeah.
Right. Now, on the surface, those two scenarios seem to have absolutely nothing in common at all.
Yeah, I mean, one is public health in the 19th century, the other is modern AAA gaming.
But, and this blew my mind, both of those people face the exact same fundamental puzzle, which is like, how do you teach a flat piece of paper or rigid silicon microchip to understand and map organic living space?
It's honestly one of the most persistent challenges in both science and computing. I mean, we are so used to the Cartesian coordinate system, right?
The old X and Y axis.
Exactly. Rigid graph paper, absolute grid lines. It's comforting because it's clean. It's binary.
Yeah, but nature doesn't work like that.
No, not at all. The natural world doesn't operate on a clean grid. Nature is organic. It's chaotic. It's defined almost entirely by proximity and relationships, not absolute coordinates.
Okay, let's unpack this. Welcome to today's deep dive. And I actually want to send a very special welcome to a specific group tuning in today.
Oh, right. The high schoolers.
Yes, a huge shout out to the Bussin' Sigma scholars of Edward Little High tuning in today.
Welcome, everyone.
We know you are in the room with us right now as our third co-host, basically. And we know you're already writing code, building projects, learning the ropes.
Doing the hard work.
But today, we are taking you way past the basics. We're going into the absolute bleeding edge of computational geometry.
It's going to be a fun ride. We're going on a journey to explore how humanity basically learned to partition space.
Which leads right up to this legendary computer graphics breakthrough, the Worley noise algorithm.
And we won't just talk theory. We're going to break down how to actually build an interactive Worley generator.
Specifically in the CMU CS Academy sandbox.
Right, and then we'll look at how modern bare metal compilers handle that exact same math under the hood.
We have a massive stack of sources today on the table. Like, we're pulling from philosophical texts dating back to 1644.
We've got Stephen Worley's foundational 1996 paper on cellular texture basis functions.
Which is a mouthful, but we'll get into it. We also have the strict architectural documentation from Carnegie Mellon University.
And some highly advanced academic literature on dimensional type systems and multi-stage MLIR compilation.
So yeah, we have our work cut out for us to really grasp how we teach computers about proximity. I want to start way back in the historical record.
Let's do it.
Because, reading through these notes, this idea of dividing space based on like what is closest, it didn't start in a 1990s computer lab.
No. It goes back much further.
It started with the French philosopher René Descartes in 1644, which is wild.
It really is.
I mean, he's famous for, I think, therefore I am. But what was he doing messing around with spatial geometry?
Well, he was basically trying to explain the entire cosmos.
As you do in the 1600s.
Exactly. And keep in mind, this is decades before Isaac Newton published his theories on gravity.
Oh, wow. So they didn't even know how gravity worked yet.
Right. So Descartes is looking up at the sky, trying to figure out why planets orbit stars. Like, how is matter actually distributed through the universe?
Without gravity, that's a tough puzzle.
So he proposed this theory of vortices. He visualized the universe as being filled with this fluid-like substance.
Oh, okay, like a cosmic ocean?
Yeah, and he argued that every star was the center of a swirling vortex of this fluid.
I'm looking at some of the illustrations from his 1644 text right now, the Principia Philosophiae. It literally looks like a giant, tightly packed jar of bubbles.
That is a really great way to visualize it.
Yeah, like some bubbles are huge, some are small, but they're all pressing up against each other, creating these really distinct cellular walls.
And that's the key. Descartes argued that the boundaries between these cosmic bubbles were defined by whichever star had the dominant pull in that specific region.
Okay, so if I'm floating in space...
Right, if you are in this patch of space, you belong to star A simply because you are closer to it than star B.
Wow, so it's all about proximity.
Exactly. Now, he didn't have the rigorous algebraic math to define the exact geometry of those borders, obviously.
He was just kind of eyeballing it conceptually.
He was operating purely on intuition, but it was a massive leap. He was partitioning the universe based on proximity to a set of generator points, which were the stars.
It's honestly incredible that the foundational logic for modern video game rendering started as this pre-Newtonian theory of astrophysics.
It's a great lineage.
But, this concept didn't just stay locked up in theoretical physics, because the sources jump forward to 1854, coming down to Earth in a very grim, practical way in London.
Yes. The John Snow cholera map.
Right, the Soho cholera epidemic. So at the time, the prevailing medical consensus was this thing called the miasma theory, right?
Yeah. The greatest medical minds of the time legitimately believed diseases were spread by foul, polluted air.
Like bad smells from swamps and slums.
Exactly. The idea was if you breathed the bad air, you got sick.
But Dr. John Snow is not buying it at all.
No. He suspected the water supply was the actual vector for the disease.
So what did he do? Because he couldn't see the bacteria.
He did something revolutionary for epidemiology. He took a physical map of the Soho district and he plotted the locations of all the public water pumps.
Okay, so in our geometric terms, those water pumps became his seeds, or like his generator points.
Exactly. Then he went door to door and mapped the locations of every single person who had recently died from cholera.
Now, if I'm Jon Snow, my first instinct would probably just be to, draw a circle around the pump with the most deaths and say, look, a cluster.
And that's what most people would do.
Yeah.
But he did something much more geometrically advanced.
Because drawing a simple circle assumes people can just fly over buildings like crows, right?
Exactly. Snow realized people have to actually walk down streets. So he didn't just draw a radius.
Right. He calculated the walking distance.
Through the actual streets of London, between the highly suspected Broad Street pump and all the other surrounding pumps in the neighborhood.
That is so tedious, but so brilliant.
And then he drew a very specific boundary line that represented the exact midpoint of walking distance between Broad Street and every alternative water source.
Let me make sure I'm visualizing this correctly for the listeners. He essentially mapped an area of equidistance.
Yes, precisely.
So if a citizen lived anywhere inside that specific kind of jagged boundary line he drew, the Broad Street pump was mathematically their absolute closest source of water.
Right, and if they lived even 1 foot outside that line,
a completely different pump was closer.
You've got it. And the real revelation came when he overlaid his mortality data onto this newly partitioned map.
Oh, I can guess what happened.
The vast, overwhelming majority of the cholera deaths fell perfectly inside that specific spatial boundary he had drawn around the Broad Street pump.
Wow. So he used geometry to literally prove that cholera mortality was directly correlated with proximity to a contaminated well.
Which fundamentally changed how we understand public health and epidemiology forever.
So we have Descartes mapping stars and Snow mapping a plague using literally the exact same underlying logic. But, when I look at the sources, they don't call these snow regions or Descartes bubbles.
No, the formal term is universally a Voronoi diagram.
So how do we get to the formal mathematics of it all?
It happened in 2 distinct stages. First, in 1850, a German mathematician named Peter Gustav Lejeune Dirichlet systematically defined these regions in 2 and 3 dimensions.
You might hear them called Dirichlet tessellations sometimes.
You will occasionally hear that, yes, especially in older texts, he was studying quadratic forms at the time.
But Voronoi is the name that stuck.
Right, because the mathematician who generalized the concept to an arbitrary number of dimensions was the Russian mathematician Georgy Voronoi in 1908.
Arbitrary number of dimensions, meaning it works in 2D, 3D, 4D, and vastly higher conceptual spaces.
Exactly. Voronoi is the one who locked down the hard algebraic proofs, defining the stability and combinatorial structures of these cells across any dimension.
Okay, let's make sure our Edward Little High scholars have an absolutely crystal clear, intuitive picture of what a Voronoi diagram is just before we start writing code for it later.
That's a good idea.
I was thinking about this earlier, and I kind of like to use a pizza delivery analogy.
Oh, I'm listening. That sounds highly relatable.
Right. Okay, so imagine a map of your city, and let's say there are 5 pizza shops scattered randomly around town.
Okay, those 5 shops are your seeds.
Exactly. Now, the pizza company wants to draw delivery zones so that every single house in the city is assigned to the absolute closest shop because, they want the pizza arriving hot. Efficiency is everything.
So how do you actually draw the borders on the map?
Well, you start by comparing just 2 shops. The boundary line between shop A and shop B is drawn exactly halfway between them.
A perpendicular bisector.
Yeah. If you stand anywhere on that specific line, your distance to shop A and shop B is identical.
You could get a pizza from either one in the same amount of time.
Right. But the moment you take a single step to the left of that line, you are definitively in shop A's territory.
So a Voronoi diagram is what happens when you do that everywhere.
Exactly. It's what happens when you draw those halfway borders between every single pizza shop in the city simultaneously. The whole space perfectly fractures into these geometric cells, one for each shop.
And if you're standing inside a specific cell, you are closer to that cell's seed than to any other seed in existence.
That's the golden rule.
That analogy holds up perfectly. And it really highlights something crucial. The borders are defined by the collision of expanding areas of influence.
It's like watching soap bubbles expand until they smash into each other.
Exactly. And once Voronoi published the formal math in 1908, applied scientists across vastly different disciplines suddenly realized they desperately needed this specific geometry.
The notes mention a crazy variety of applications. Like, in 1911, an American meteorologist named Alfred Thiessen used this exact math to estimate regional rainfall across huge areas.
And he did that based on just a few scattered rain gauges, right?
Yeah, and meteorologists literally still call them Thiessen polygons today.
It's incredible. And then in 1933, physicists Eugene Wigner and Frederick Seitz used Voronoi partitioning to model the packing configurations of atoms inside crystal lattices.
Wait, so crystals are basically just atomic Voronoi diagrams?
Yes. When you look at the microscopic structure of a crystal, the atoms arrange themselves into these exact cellular boundaries, which we now call the Wigner-Seitz cell.
That is mind-blowing. And even our smartphones rely on this, right?
Absolutely. When cellular network engineers are placing physical cell towers across a city, they model the towers as seeds in a massive Voronoi diagram.
So as you ride the bus to school, your phone is just constantly evaluating its position against those invisible Voronoi borders.
Yep, to seamlessly hand off your call to the closest tower, the math is everywhere you look.
It even extends beyond physical reality into abstract mathematics, because the sources touch on this thing called high-dimensional Poisson-Voronoi tessellations.
Right, that's where it gets really abstract.
I'm going to need you to translate that into English for me. High-dimensional space.
Sure. So, when mathematicians calculate Voronoi partitions in 2D, like your pizza map, the cells are jagged, kind of eccentric polygons, right?
Yeah, they look like shattered glass.
But when you start calculating them in 50, 100, or 1,000 mathematical dimensions, which, by the way, we use constantly in advanced machine learning and data clustering,
Oh, wow, okay.
the geometry actually undergoes a fascinating phase transition. As the dimensions increase, the cells actually lose their jaggedness.
They get smoother.
They become highly structured, wildly symmetrical, almost crystalline spheres. It's beautiful, mathematically speaking.
So the chaos of 2D space just sort of smooths out into profound order in high dimensions.
Exactly.
Okay, I have to jump in and play devil's advocate here on behalf of our students.
Go for it.
Because it is undeniably fascinating that this single mathematical concept explains Descartes' cosmic theories, Jon Snow's cholera maps, crystal atoms, and cell phone towers.
It's a unifying theory in a way.
But our Bus and Sigma scholars are studying computer science. They want to render graphics. They want to build applications. Why on earth does a video game engine care about 19th century epidemiology maps?
That is the million-dollar question. And the answer is because the natural world is profoundly fractured.
Fractured? How so?
Well, for a very long time in early computer graphics, the absolute gold standard for generating procedural textures was gradient noise.
Like Perlin noise.
Exactly. The most famous example is Perlin noise, invented by Ken Perlin in the 1980s for the movie Chiron.
I've actually played around with Perlin noise before. It generates these incredibly smooth, undulating gradients.
It does. It's very continuous.
Like if you map it to a terrain generator, you get beautiful rolling hills. Or if you map it to transparency, you get these soft, wispy clouds. It's fantastic for anything that transitions smoothly.
But standard Perlin noise fails completely when you attempt to model discrete, cellular, or fractured materials.
Ah, I see.
Think about the texture of cracked mud in a dry riverbed. Or think about a flagstone path, or the microscopic cellular structure of a leaf.
Or like reptile scales, or crushed ice.
Exactly. Nature is full of sharp borders and distinct organic regions.
And smooth gradients just cannot replicate a sharp crack.
They physically can't. So to render the real world, graphics programmers realized they desperately needed the mathematics of Voronoi.
Which brings us to 1996. This is a massive turning point in the
A
sources.
watershed moment for computer graphics.
A researcher named Stephen Worley publishes a paper at the SIGGRAPH Computer Graphics Conference, and it's titled A Cellular Texture Basis Function.
This paper literally revolutionized procedural generation. Worley understood that Voronoi diagrams were the mathematical key to rendering organic textures.
But he ran into a brutal wall, didn't
He
he?
did, because true Voronoi diagrams are computationally devastating to calculate in real time.
Let's break down why it's so devastating, because I saw the phrase ON complexity problem in the notes, and for a student writing a rendering loop, what does that actually mean?
Okay, imagine you're rendering a texture for a modern video game, and you need to calculate the color of a single pixel on the screen.
Just one pixel.
Right, and let's say you have randomly scattered 100 seeds, your pizza shops, across your digital canvas.
Okay, I have my 100 seeds.
To figure out which seed is closest to your current pixel, the naive approach requires you to calculate the distance from your pixel to seed 1,
Okay.
then seed 2, then seed 3, all the way to seed 100.
Wait, 100 distance checks for just one pixel?
Yes. You evaluate all 100 distances, find the absolute minimum value, and that tells you your closest seed. Then you move to the next pixel on the screen and do it all over again.
So if I have like a standard 1080p monitor, that's roughly 2 million pixels.
Give or take, yeah.
Multiply that by 100 distance checks per pixel. My computer is performing 200 million mathematical operations just to draw one single frame of a cracked mud texture.
Exactly. And if you want the game to run at 60 frames per second,
My CPU is instantly going to melt. It literally can't keep up.
and keep in mind, 1990s processors were vastly slower than what we have today.
Oh, right. So doing 200 million checks per frame in 1996 was basically science fiction.
Calculating true, mathematically perfect Voronoi noise across a screen was utterly unfeasible for real-time applications. So Worley had to figure out a way to cheat the math.
How do you cheat a mathematical absolute, like, distance? Like, it is what it is.
You don't cheat the distance itself. You restructure how the seeds are distributed in the first place.
Okay, walk me through that.
In a true Poisson distribution, which is just true randomness, seeds can randomly clump together in one corner of the screen.
Right, randomness doesn't mean evenly spread.
Exactly. It can leave huge empty voids elsewhere. So Worley threw out true randomness. Instead, he overlaid a rigid, invisible grid across the entire digital canvas. Think of a massive chessboard.
Okay, I have my invisible grid in my head.
Then he instituted an unbreakable rule. There must be exactly one randomly placed seed somewhere inside every single square of that grid.
Ah, I see. The seeds are still placed at random coordinates, but their randomness is mathematically bounded.
Exactly.
Like a seed can wander anywhere inside its designated grid square, but it absolutely cannot cross into a neighboring square. This totally prevents the clumping.
Bounding the randomness was his masterstroke. Because once the computer knows that there's guaranteed to be exactly one seed in every single grid cell, it unlocks a massive algorithmic shortcut.
I love a good optimization. It's a shortcut.
Now, when the computer evaluates a specific pixel, it doesn't need to calculate the distance to all 100 seeds on the canvas. It simply checks which grid square the pixel is currently sitting inside.
Because the closest seed geographically must be either the seed inside that exact same grid cell or a seed in one of the immediately adjacent neighboring cells.
Precisely. It's the 9-cell check.
Oh, wow, yeah. You only need to check the current cell plus top left, left, right, bottom, and bottom right.
9 total checks.
Instead of 100 distance checks per pixel, the computer only ever has to perform 9. That is an absurd reduction in workload.
It really is. It drops the time complexity from an operation that scales linearly with the number of seeds, which is ON, to a constant time operation, O1.
Because it doesn't matter if you have 100 seeds or 10 million seeds on your vast canvas, evaluating a single pixel always takes exactly 9 checks.
Exactly. It's a beautiful piece of logic.
But wait, I have a question on the implementation here. If we have to keep track of the coordinates for millions of seeds in memory, aren't we just trading a CPU bottleneck for a RAM bottleneck? Like, storing all those X and Y coordinates would take a lot of memory.
That is an excellent observation, and Worley absolutely thought of it.
So how did he fix it?
He didn't store the seed coordinates in memory at all.
Wait, what? Where did they go?
He generated them on the fly using something called a linear congruential generator, or LCG.
I've seen LCGs mentioned in cryptography, but how does it work for generating texture coordinates?
An LCG is one of the oldest and fastest algorithms for generating pseudo-random numbers. It relies on incredibly simple math, modular arithmetic, and prime numbers.
Okay, so you don't need a huge random number lookup table.
Exactly. You just take a seed value, in this case, the integer coordinate of the grid cell itself, like cell 5, 10.
Right.
You multiply it by a massive prime number, add another prime number, and then find the remainder when divided by a modulus.
Because the math is so basic, it takes almost 0 CPU cycles to execute?
Exactly. So instead of looking up the coordinates of a seed in an array, the graphics card just runs the LCG equation using the grid cell's ID, and it instantly spits out the pseudo-random x and y position of the seed inside that cell.
It's actually faster to do the math than to read from memory.
It is brilliant
Gee.
optimization. The CPU doesn't wait around for RAM at all.
And once Worley solved the processing bottleneck, the true visual magic came from how he evaluated those 9 distances, right?
Yes. The algorithm doesn't just find the single closest seed and stop, it sorts them.
Okay, so it ranks the 9 seeds.
It calculates a value called F1, which is the distance to the absolute closest seed. But it also calculates F2, the distance to the second closest seed.
And F3, the third closest, and so on.
Exactly.
I was looking at the visual outputs and the sources, and the difference between F1 and F2 is staggering. Like, if you just tell the computer to output the F1 distance as a grayscale color where a distance of 0 is black and further away is white, you get this bumpy, bubbly texture.
Yeah, it looks a bit like a petri dish full of dividing cells, or a microscopic view of tissue.
It's cool, but it's not revolutionary.
But Worley realized you can perform mathematical operations between those sorted values.
So what happens if you take F2 and subtract F1?
That's where the magic happens.
Right. If you calculate F2 minus F1, the math does something incredible right at the borders. Let's go back to the pizza shops for a second.
Always a good idea.
If I am standing exactly on the borderline between shop A and shop B, my distance to my closest shop F1 and my distance to my second closest shop F2 are absolutely identical.
Therefore, mathematically, F2 minus F1 equals exactly 0.
Yes. And if 0 is mapped to the color black, the algorithm renders a perfectly crisp, pure black line exactly at the geometric border between every single cell.
Because everywhere else in the cell, F2 is going to be larger than F1.
Right, so as you move away from the border and deeper into a cell, the difference between F2 and F1 grows larger, making the pixel brighter.
And the visual result is a texture that looks exactly like a network of sharp, deep cracks.
It is the ultimate procedural algorithm for generating cracked mud, shattered glass, or biological membranes. It looks so organic.
Worley called this the generalized cellular texture basis function because he realized you aren't limited to just subtraction.
Oh, you can do other math.
You can multiply F1 by F2. You can square them, invert them, or blend them with varying coefficients. By altering the mathematical relationship between the closest seeds, you open up an infinite superset of organic textures.
Like wood grain or marble or lunar craters.
Exactly. The possibilities are endless.
And, reading through his 1996 paper, you really realize what an absolute master of bare metal optimization Worley was.
He was a true hacker in the best sense of the word.
Because in the 90s, CPUs were terrible at handling floating point decimal numbers. Right?
Very slow, yeah.
So Worley built his entire algorithm using fixed point integer arithmetic. Furthermore, he realized that calculating true distance requires the Pythagorean theorem.
A squared plus b squared equals c squared.
Right, and to find c, the true distance, you have to calculate a square root.
And square roots are notoriously brutal for a processor to calculate. They eat up so many clock cycles.
So how did he avoid it? Because you need distance.
He just didn't use them.
He skipped the square root entirely.
He reasoned that if you're merely trying to figure out which seed is the closest among the 9 neighbors, you don't actually need the true distance.
Wait, you just need to compare them.
Exactly. You just need to compare the square distances. If distance a squared is a smaller number than distance b squared, then true distance a is definitively smaller than true distance b.
Oh, that is so smart.
He performed all of the sorting and comparisons using purely squared distances, completely bypassing the square root operation until the very final step, when he needed to output a smooth color gradient.
It's the kind of lateral thinking that really separates a good programmer from a great computer scientist. You analyze the mathematical rules, and you find the loopholes that the hardware can exploit.
Optimization is an art form.
It really is. And because Worley solved the CPU bottleneck and optimized the math, digital artists finally had the tool they needed to render the organic world. But, knowing the theory's great, seeing it applied in blockbuster media really drives home its power.
It's everywhere now.
So how are modern rendering pipelines utilizing Worley noise today? Let's talk about some real-world applications.
We can look directly at Guerrilla Games and their proprietary Nubis rendering engine.
Oh, they built this engine for the AAA video game Horizon Zero Dawn, right?
Yes, and that game was widely lauded for having some of the most breathtaking, realistic, real-time, volumetric skies ever programmed in a video game.
I remember playing it and just staring at the sky, but rendering a cloud in real time sounds like an absolute nightmare.
It is. It's not a solid 3D model made of polygons that you can just paint a texture onto. It's a volume of space filled with millions of suspended water droplets, scattering light in every direction.
So how do they even render that?
It requires a technique called ray marching. The camera shoots a ray through a 3D texture, sampling the density of the cloud at hundreds of points along the ray to simulate how light penetrates and bounces inside the volume.
Which sounds immensely computationally expensive.
Incredibly so. And before Horizon Zero Dawn, most games generated their clouds using standard fractal Brownian motion.
Which is just what? Layering different frequencies of Perlin noise on top of each other?
Essentially, yes. Now, Perlin noise is great for cirrus clouds, those thin, wispy streaks of cotton high up in the sky.
Right.
But standard Perlin noise completely fails to generate massive, towering cumulus clouds.
Why is that?
Because cumulus clouds have dense, billowing bulges. They look like cauliflower.
Right, they have structure.
Perlin noise just creates undulating hills. It lacks the tight, clustered spheres of density required to give a storm cloud its visual weight and menace.
So the engineers at Guerrilla Games looked to Stephen Worley.
They did. They generated a 3D field of Worley noise. But they did something incredibly clever with the math. They inverted it.
They inverted the output.
Yes, instead of taking the F1 value as the density, they calculated 1 minus F1.
Okay, let's visualize that math for the scholars. If you invert the output, the dark, sharp cracks at the boundaries suddenly become bright, sharp ridges, right?
Exactly.
And the bright, bubbly centers of the cells become deep, dark valleys.
Who's got it? So in map to 3D volume, 1 minus F1 creates these tightly packed, distinct billowed shapes that look incredibly structural.
Like the cauliflower bulges of a cumulus cloud.
Exactly.
Yeah.
But here's a catch. If you just render inverted Worley noise on its own, it looks artificial. It looks like a pile of plastic spheres or literal bubbles floating in the sky.
Because it's too perfect. It lacks the organic, wispy edges of a real cloud.
So they synthesized the two algorithms.
No, this is the good stuff.
They took the wispy, connected flow of Perlin noise, and they used the inverted 3D Worley noise to literally dilate it. They effectively used the structural boundaries of the Worley cells to push, warp, and gather the Perlin noise into dense, cauliflower-like clusters. They forged a brand new hybrid algorithm they named Perlin-Worley noise.
It's a brilliant synthesis. You get the structure from Worley and the wispiness from Perlin.
Exactly. And this desire to bridge the gap between smooth gradients and sharp cellular structures is a huge area of ongoing research.
I was actually looking at the notes on Inigo Quiles. He's a legendary programmer in the computer graphics world.
His work on shaders is phenomenal.
Yeah, he wrote extensively about this in the Book of Shaders. He created a unified algorithm he literally calls Voronoi.
Which is a perfect portmanteau of Voronoi and noise.
Right. So Quiles asked a very fundamental philosophical question about the math. Perlin noise interpolates values smoothly based on a grid.
Right.
But Voronoi noise strictly evaluates the absolute minimum distance to a set of points. On paper, they appear to be completely opposed operations.
One is smooth, one is fractured.
But Quiles hypothesized that they are actually just two extreme ends of a single generalized grid-based metric.
And he proved it mathematically.
He did. He developed a weighting function that changes how a pixel interacts with the seeds. Because in standard Voronoi, a pixel only cares about the single closest seed.
It ignores everything else.
Right. But in Quiles Voronois, a pixel looks at all the nearby seeds and calculates a weighted contribution from every single one of them based on inverse distance.
So if a pixel is extremely close to a seed, that seed dictates almost all of the pixel's color.
But a seed further away still exerts a tiny bit of gravitational pull on the pixel, effectively softening the sharp mathematical border.
By exposing this weighting function as a tunable parameter, Quiles created a slider.
which is so cool for artists. If you pull the slider all the way to one side, you get pure, smooth, Perlin-style noise.
And if you pull it to the other side, you get sharp, fractured Voronoi cells.
And if you put it right in the middle, you get this beautiful, semi-structured, organically melting texture. It is a stunning piece of mathematical unification.
And, it brings us full circle back to the biological roots we discussed earlier.
With the cholera maps and the skin cells.
Exactly. In cellular biology, researchers use the term cellular noise to describe the random variability in protein expression among genetically identical cells.
Yeah, the notes mention that it's statistically defined as when the variance divided by the mean equals exactly 1. It is literally a mathematical measurement of biological randomness.
And look at what these graphics programmers are doing. They are writing algorithms that precisely balance statistical randomness with structured mathematical control.
They are literally programming cellular noise to perfectly mimic biological tissue. It is such a profound convergence of biology, math, and art.
It really is.
Okay, we've covered the history, the mathematical optimization, and the AAA video game applications. Now comes the most important part of today's deep dive.
Time to build it.
Yes. For the Bus and Sigma scholars of Edward Little High, it is time to put theory into practice. Get your keyboards ready. We're going to walk through the technical implementation of building an interactive Worley noise generator.
Using Python inside the CMU CS Academy sandbox.
Specifically, we are operating in CPCS mode.
Right. CPCS stands for College Programming and Computer Science. It is an advanced, highly structured environment provided by Carnegie Mellon University.
And it enforces a very specific, uncompromising architectural standard, right?
Yes. MVC. Model View Controller.
I can already hear the collective groan from the students when they hear MVC.
It has a reputation.
If I'm a student writing Python code right now, I'm probably pulling my hair out asking, why is this MVC rule so strict? It feels like it takes 10 extra lines of code just to draw a simple square. Why can't I just tell the computer to draw a pixel exactly when I want it to?
I completely understand the frustration. When you are first learning to code, you just want things to appear on the screen immediately.
Right, instant gratification.
But as you transition to elite computer science, you realize that tightly coupling your data to your graphics is a recipe for catastrophic failure in large systems.
How so?
If you blur the lines between your data, your drawing logic, and your input handlers, you create spaghetti code. State gets desynchronized. You get race conditions.
And in CPCS mode, they don't even let you make that mistake, do they?
No. If you attempt to bypass MVC, the framework will literally throw a runtime error and crash your program. It forces you to build robust, scalable architecture from day one.
Okay, let's respect the architecture and break this down step by step. We are building a Worley noise generator. The first pillar is the model.
Yes.
Where does our raw data actually live?
In the CMU framework, the model is initialized inside a specific function called onAppStart.
And that app parameter is important.
Crucial. The app parameter is a global state object. It is automatically passed into every single screen, event handler, and drawing function across your entire program.
It's like the backpack carrying all your data.
Exactly. And the model is where you define the physical reality of your simulation. It draws nothing. It only stores facts.
So inside onAppStart, we need to define our grid configuration first. We tell the system how large our canvas is. Let's say app.width equals 400 and app.height equals 400.
Standard canvas size. Next, we need to generate our seeds.
Right. We can use a simple for loop to create a list of random x and y coordinates and store them in a list called, let's say, app.seeds.
But we don't just want a static image, right? We want animated, living noise.
Oh, yeah. So we shouldn't just give the seeds static coordinates. We should give them velocity vectors.
Exactly. For every seed, generate a random dx and del speed value and store that with the coordinate. Now, the seeds have the potential to drift around the screen like microorganisms.
I love that. We also need to store the user's state. So let's create a variable called app.mode equals 1, which will track whether the user wants to render the F1 distance, the F2 distance, or the F2 minus F1 border mode.
Good call. And we can also add a Boolean flag, app.paused, false.
Okay, that is our entire model, just raw data sitting in memory.
Next up is the controller.
Right, the controller houses all the logic that mutates the model over time or responds to user input. The primary engine here is the onStep app function, right?
By default, the CMU framework calls onStep 30 times every single second, dictated by the app.steps per second property.
So inside onStep, we write the logic to animate our seeds. We first check if app.paused is false. If it is, we loop through our app.seeds list.
And you add the dx velocity to the seed's x-coordinate and the yd velocity to the y-coordinate.
But wait, if they just keep moving, won't they eventually drift right off the edge of the screen?
They will, which is why you must add bounds checking.
Ah, okay.
If a seed's x-coordinate exceeds app.width or drops below 0, you just multiply its dx velocity by -1.
Oh, so the seed just bounces off the invisible wall.
Exactly, keeping our noise dynamic and contained within the canvas.
We also need controllers for user input. We can define on-key press, app, key.
Yes. We can write a simple if statement. If the user presses the 1 key, app.mode becomes 1. If they press 2, it becomes 2. If they press 3, it becomes 3.
And if they press P, we toggle the app to pause Boolean to freeze the animation.
Perfect. Let's add mouse interactivity too with on-mouse press app, mouse X, mouse Y.
Okay, when the user clicks the canvas, we want to grab the nearest seed and instantly teleport it to the mouse's location. That sounds interactive.
So inside on mouse press, we loop through app.seeds, calculate the distance from the mouse to each seed.
Using squared distances, obviously, to channel our inner Stephen Worley and save CPU cycles.
Naturally, you find the closest one and update its X and Y properties to equal mouse X and mouse Y.
Now, let's stop and look at what we have accomplished. We have a fully functioning simulation running in memory. The seeds are moving, bouncing, responding to keyboard and mouse clicks.
But we have not drawn a single pixel to the screen.
Which brings us to the final pillar, the view. In CTCS mode, all visual rendering must happen exclusively inside the redraw app function.
The CMU documentation is absolutely adamant about this.
Why is it so strict about redraw?
Because on every single frame, the framework completely wipes the canvas blank. It erases everything. Then it calls redraw app. You never write code to manually erase old shapes. You only ever draw the current slice of time.
So how do we render the Worley cells? We use nested for loops to iterate over the X and Y coordinates of the canvas.
But keep in mind, because we're running Python in a web browser sandbox, calculating distance for every single individual pixel might cause lag.
Oh, right. It's not a compiled C++ engine. So as an optimization, we can iterate in blocks of, say, 5 by 5 pixels.
That's a great compromise. For each 5 by 5 block, you calculate the distance to all the seeds in app.seeds.
Then you sort that list of distances from smallest to largest. The first item in that list is your F1 value. The second item is F2.
Then we evaluate app.mode.
Right. If the mode is 1, we map the F1 distance to a grayscale color value. A shorter distance yields a darker color.
And if the mode is 3, we calculate F2 minus F1, mapping the result to our grayscale to reveal the sharp, cracked Voronoi borders.
Once you have calculated the final color string, use the CMU graphics primitive drawrect, XY width, height, fill color, to paint the 5 by 5 block onto the canvas.
You could even utilize the built-in gradient functions like gradient black-white start center for more complex visual texturing.
That would look amazing. And as a final polish, after drawing all the blocks, we can run one more quick loop through app.seeds and use draw circle, seed.x, seedbot3, filled, to draw a tiny red dot exactly where each generator point is located.
That's a great debugging tool, and it looks cool.
Yeah, because when you run this program, you will literally see the invisible red seeds bouncing around the screen, mathematically warping and pulling the grayscale cellular walls around them in real time. It is incredibly satisfying to build.
It is a phenomenal way to internalize the geometry. But I do want to revisit a point of friction you brought up earlier about MVC.
Oh, the desire to draw outside of redraw?
Exactly. Let's say a student is writing on mouse press, app, mouse X, mouse Y. They know exactly where the mouse was clicked. They have the coordinates right there in the function.
Right.
Why can't they just calculate the new color and call drawRect right there inside the on mouse press function? Why wait for the frame to end and force redraw to do it?
Yeah, from a beginner's perspective, it feels horribly inefficient to update a variable, wait for the engine to loop around, wipe the whole screen, and redraw everything just because I clicked one pixel.
Attempting to call drawRect inside on mouse press is a fatal MVC violation. If you do it, the CPCS framework will instantly kill your program.
Brutal. But why?
Here is why. The view must be a pure, deterministic reflection of the model at a frozen slice in time. If you allow a controller to hijack the rendering pipeline and draw it to the screen asynchronously, you introduce massive instability.
Oh, I see. What happens if OnStep is moving a seed at the exact millisecond on mouse press is trying to draw it?
Exactly. The state becomes desynchronized. You end up with phantom pixels on the screen that have no underlying data supporting them. By enforcing that drawing only happens in redrawal, the architecture guarantees that the visual output is always a mathematically perfect representation of the data.
That makes total sense when you frame it around system stability. You have to respect the MVC architecture. Now, building this procedural generator in Python inside a web browser is an amazing educational exercise for scholars.
It's the best way to learn the logic.
But Python is an interpreted language. It has inherent overhead. When Guerrilla Games is ray-marching volumetric clouds at 60 frames per second in 4K resolution on a PlayStation, or when engineers are calculating spatial partitioning on a neuromorphic chip,
A Python for loop is going to crash and burn.
it wouldn't even render a single frame. To achieve AAA gaming performance or to run on embedded hardware, you need bare metal speed. You need code that is sculpted to the exact microscopic architecture of the silicon processing it.
Which transitions us perfectly to the final, most advanced portion of our deep dive.
Yes. We are looking at a bleeding-edge academic paper detailing a programming language called Clef and its accompanying compilation framework called Fidelity.
This paper introduces two revolutionary concepts that elevate code from mere logical instructions into hardware-aware physical engineering. Those concepts are dimensional type systems, or DTS, and deterministic memory management, DMM.
Okay, let's start with dimensional type systems, because I'm looking at the notes on DTS, and frankly, I was a bit lost when I first read it.
It's a very advanced concept.
In standard programming, if I declare a variable as a float, it's just a decimal number, right?
A slot in hardware holding ones and egos.
The compiler doesn't know what that number represents in the real world. Is it 5 meters? Is it 5 seconds? How could the compiler possibly know the physical dimension, and why does it even matter? Doesn't all that human context vanish when it compiles down to machine code anyway?
In traditional compilers, yes, that context vanishes entirely. It's a phenomenon called early erasure. The compiler strips away the physical meaning and just crunches the raw numbers. But the Clef and Fidelity framework is designed for cyber-physical systems. These are programs that interact with physical reality across heterogeneous hardware.
Like a sensor pipeline routing data from a CPU to an FPGA accelerator to a neuromorphic chip.
Exactly. In Clef, the physical dimensions meters, seconds, kilograms, are mathematically bound to the variable types using abelian groups and linear algebra.
Okay, stop there. Abelian groups. Linear algebra. How does that work in practice?
Think of it like this. In real-world physics, you cannot add meters to seconds.
Right, it makes no physical sense. You can multiply them to get meters per second, but you can't add 5 meters to 5 seconds.
Exactly. An abelian group is a mathematical concept that defines a set of elements and an operation that combines them, ensuring commutativity, meaning A plus B equals B plus A.
Okay, I'm with you.
By mapping physical dimensions to abelian groups, the Clef compiler uses linear algebra to mathematically verify your equations before the code ever runs.
Wow. So if your Worley noise algorithm accidentally tries to add a spatial distance to a time variable,
The compiler mathematically proves the equation is invalid and throws a compile time error.
that sounds like an incredible way to prevent catastrophic bugs, like that famous Mars climate orbiter that NASA lost because one engineering team wrote their software using metric newtons and another team used imperial pound seconds.
Exactly. The math ran perfectly on the computer, but the physical reality was fatally mismatched.
DTS prevents those errors entirely. But reading further, bug prevention is just a side effect, isn't it?
Yes, the true power of DTS is how the compiler utilizes that dimensional data to optimize the hardware. In the Clef framework, these dimensional annotations actually survive through a complex 5-stage MLIR lowering pipeline.
Let's unpack MLIR for a second. It stands for Multi-Level Intermediate Representation. For our students, think of a compiler like a translator.
A great analogy.
Translating Python source code directly into Silicon machine code is like trying to translate a massive novel from English directly into ancient Sumerian in one single pass. It's way too complex, and you miss opportunities to optimize the grammar.
Exactly. MLIR breaks the translation down into distinct, manageable steps.
So what are the 5 stages in Clef?
First, you have your human-readable source code. Second, it translates into a typed abstract syntax tree. Third, it lowers into a program semantic graph, or PSG, which is really the beating heart of the system.
Okay.
Fourth, it lowers into standard MLIR. And finally, fifth, it translates into the target dialect specific to the exact microchip you are using.
And because Clef preserves the physical dimensions all the way down into that program semantic graph, the compiler can perform a miracle called representation selection.
Representation selection is profound. Let's look at our Worley noise algorithm again.
Okay.
If the compiler knows, mathematically, because of DTS, that a variable represents a fractional spatial distance constrained between 0.0 and 1.0,
It knows the value will never be -1 million. It will never be 3 billion. It's strictly between 0 and 1.
Right. So why on earth would the computer waste memory and transistor power assigning that variable a standard 64-bit IEE floating point representation?
Because floating point numbers are designed to handle values as massive as the distance between galaxies, right? It's massive overkill for a grid bounded between 0 and 1.
You wouldn't do it. The Clef compiler analyzes the dimensional bounds of your math, realizes a float is incredibly wasteful, and automatically selects a vastly superior hardware representation like posit arithmetic.
Posit arithmetic. This is one of the most fascinating concepts in the whole stack today. Can you break down how posits actually work at the bit level? Because the notes say they use a variable length regime.
To understand posits, you first have to understand why standard floats are flawed.
Okay, lay it on me.
Standard floating point numbers distribute their precision relatively uniformly. They dedicate a fixed number of bits to the exponent, which is the scale of the number, and a fixed number of bits to the fraction, the decimals.
Okay.
So they give the exact same amount of fractional precision to the number 1.0 as they do to the number 1 milson.
But posits don't use fixed allocations. They use a variable length regime, which creates tapered precision.
Exactly. A posit dynamically steals bits from the exponent and gives them to the fraction, but only when the number is close to 1.0.
Wait, so the closer the value is to 1 or -1, the more decimal bits it gets?
Yes. It concentrates a massive, laser-focused amount of decimal precision right around 1.0 and sacrifices precision at the extreme, massive, or microscopic ends of the scale.
Which is absolutely tailor-made for bounded spatial calculations, like our Worley noise grid where distances are naturally constrained between 0 and 1.
Precisely. The compiler sees the dimensional bounds of your Voronoi math, recognizes the critical values hover near 1.0, and automatically compiles the code to use posit arithmetic instead of floats.
That is genius.
This allows the algorithm to run wildly faster, consuming vastly less electricity, especially on specialized hardware like FPGAs, field programmable gate arrays.
It basically achieves higher precision where it actually matters visually, using fewer physical bits of RAM.
Yes, and speaking of RAM, that brings us to the second major innovation of the Fidelity compiler, DMM, Deterministic Memory Management.
Memory allocation is usually the silent killer of performance in an application, isn't it?
It is often the biggest bottleneck by far. Every time you create an array like our grid of Worley cells, the computer has to decide where it actually lives in physical RAM.
Does it go on the stack? Because the stack is incredibly fast, but it is temporary, right? It gets wiped when the function finishes.
Right. Or does it go on the heap? The heap is large and permanent, but it's much slower to access.
And in languages like Java or Python, the heap requires a garbage collector to periodically freeze the program and clean up unused data.
Which causes stuttering in video games.
Exactly. In standard languages, the computer mostly just guesses or forces you to rely on that garbage collector. But DMM in the Fidelity compiler uses a technique called escape analysis.
Yes, because the compiler's program semantic graph tracks the lifetime of every single piece of data. It can essentially trace the geometry of your code.
So when you allocate memory for your Worley grid, the compiler asks, does this array escape the function it was created in?
Right. Is it returned to a higher level system? Is it captured by an asynchronous closure?
The compiler traces the data's entire destiny before the code ever even runs. And the paper outlines 3 developer models for how you control this: push, bounded, and pull.
Let's run through them. The push model is explicit control. The developer writes annotations saying, I demand this array lives permanently in arena memory.
Okay, old school control. And the bounded model.
That relies on scoped inference. You define a block of code, and the compiler mathematically infers the most optimal memory layout just for that specific block.
But the pull model is where it gets super futuristic. It's total inference. The developer writes 0 memory annotations.
Not at all.
The compiler analyzes the entire global context of the program and dictates the absolute optimal memory strategy across the board.
And the tooling gives you design time feedback. You can literally hover your mouse over your code in the IDE.
And it will tell you what it's doing.
It will literally tell you, I am placing this Worley array on the slow heap because it escapes its function on line 42. But if you rewrite your logic slightly, I can place it on the ultra-fast stack and make this operation 10 times faster.
That is insane. It acts as a mentor, literally coaching you into writing elite bare metal code.
It is a profound level of optimization. And it culminates in the utilization of highly specific hardware features, like the choir.
Oh, the choir. It sounds like an ancient medieval manuscript, but it's actually a piece of silicon.
The choir is a massive 512-bit fixed-width exact accumulator.
Okay, what does that mean in English?
When you are calculating millions of Euclidean distances for Worley noise simultaneously on a Xilinx FPGA accelerator, you are constantly performing fused multiply-add operations.
Which is just doing a times b plus c, like calculating x squared plus y squared for our Pythagorean distance.
Exactly. And in a standard CPU, every time you do that multiplication and addition, the computer has to round the decimal off so the result fits back into a standard 32-bit register.
And every time it rounds, you lose a tiny slice of precision. Over millions of calculations, those rounding errors compound, creating visual artifacts in your procedural texture.
But the choir solves this through sheer brute force width.
Explain that width.
The choir is a physical 512-bit pipeline etched right into the FPGA silicon. It is so wide that it can accumulate the results of hundreds of multiplications and additions without ever dropping a single decimal of precision.
It just keeps it all perfectly accurate until the very end.
It only rounds the number once, at the very end of the entire loop, when the final pixel value is actually outputted.
And because the Fidelity compiler tracked your dimensional type system and ran deterministic memory management all the way down the MLIR pipeline, it automatically knows to route your Worley distance math directly through the choir accumulator.
Exactly. The software perfectly sculpts itself to the physical architecture of the silicon.
That is the difference between writing an instruction and engineering a system.
It absolutely is.
Which brings us to the ultimate takeaway for our Edward Little High students. Writing the Python code in the CMU sandbox is a fantastic first step.
It teaches you the algorithmic logic and the strictness of MVC. It's the proof of concept.
But understanding how the machine actually translates that logic into physical reality, how it allocates exact bits of memory, how it dynamically chooses between floats and posits based on the physics of the dimensions.
And how it utilizes specialized silicon like the choir to eliminate rounding errors.
That is what separates a standard coder from an elite computer scientist.
We have covered an astronomical amount of ground today.
We really have. We started all the way back in 1644, looking through the eyes of René Descartes as he imagined the cosmos partitioned into swirling vortices governed by stars.
We moved to the streets of London in 1854, where Dr. John Snow used the precise geometry of spatial boundaries to trace a cholera plague directly to the Broad Street pump.
We watched Lejeune Dirichlet and Georgy Voronoi lock down the rigorous formal mathematics of these regions, proving their stability from 2D pizza maps all the way up into high-dimensional space.
We explored how Stephen Worley revolutionized computer graphics in 1996. By bounding randomness within a grid, he broke the ON complexity barrier,
turning an impossible rendering task into a lightning-fast 9-cell check, while cleverly avoiding square roots entirely.
We witnessed the AAA gaming applications, breaking down how Guerrilla Games synthesized inverted Worley noise with Perlin noise to create the breathtaking volumetric storm clouds of Horizon Zero Dawn.
We mapped out the exact architecture required to build an interactive Worley generator in the CMU CS Academy, unpacking why the rigid separation of model, view, and controller is critical to preventing race conditions and keeping systems stable.
And finally, we descended all the way to the bare metal with the Clef and Fidelity compiler framework,
exploring how dimensional type systems and escape analysis empower compilers to physically reshape the hardware, utilizing posits and choir accumulators for maximum efficiency.
It has been quite the journey.
An epic journey from philosophy to epidemiology to computer graphics to the physical architecture of silicon. But before we sign off, I want to leave you, our ambitious scholars, with one final, slightly mind-bending thought to mull over.
Oh, I think they are ready for it.
We have seen that Voronoi diagrams and spatial partitioning dictate the microscopic packing of atoms in crystals through Wigner-Seitz cells.
Right.
We've seen them define the biological variants of our skin cells, the algorithms that render our virtual skies, the physical layout of our modern cellular networks, and Descartes' macrostructure of planetary orbits.
It is a mathematical pattern that scales perfectly from the microscopic atomic level all the way to the macroscopic cosmic level.
It is a universal geometric truth. So it begs a fascinating question. If nature relies so heavily on this specific mathematical optimization to govern space, is the geometry of the universe itself just a massive, high-dimensional Poisson-Voronoi tessellation?
A cosmic grid.
Exactly. When astronomers look out at the distribution of galaxy clusters separated by vast cosmic voids, Are we just observing the F1 and F2 borders of a great cosmic algorithm?
It makes you wonder.
Are we and the students listening right now just seeds navigating our own expanding spatial partitions in a universally compiled program?
If the universe is indeed computing its own existence, it is almost certainly using the most optimized algorithm available to save on processing power.
And Stephen Worley's noise algorithm might just be a glimpse into the source code of reality. Thank you to all the Bussin' Sigma scholars of Edward Little High for tuning in today. We encourage you to fire up that CMU CPCS mode, respect the MVC architecture, and start coding your own universes. Keep diving deep.